Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Hall effect and the calculation of electric conductivity and Hall coefficient by four-proof method. Let's begin. Hall effect. The scientist Edwin Hall proposed an effect. According to Edwin Hall, the statement when a current carrying conductor or semiconductor is placed in a magnetic field, that magnetic field is mutually perpendicular to the direction of current, means both magnetic field and direction of current are perpendicular with each other. As a result, a potential difference is developed. That developed potential difference at right angles to both the magnetic as well as electric field. Let me understand that effect by using four-proof method. Let us consider a rectangular semiconductor slab, which is the linear arrangement of 4 number of probes. This is a rectangular semiconductor slab. It has the length from that point to this point as W, and breadth, or we can say that is the thickness as T. T be the thickness from this to that, length into thickness. In x direction, the electric field is applied. That is electric field. Along that x direction, magnetic field along that z direction. So, electric field and magnetic field both are mutually perpendicular to each other. A current carrying conductor or semiconductor is placed in a mutually perpendicular magnetic and electric field. You supply the current, Therefore, what happened to this? So, a potential difference is developed at right angles to both the electric and magnetic field. So, electric field now along that of x direction as from positive to negative, that with the movement of electrons on the opposite direction of that of flow of current, and magnetic field along z direction is the magnetic field along z direction and electric field along x direction. Therefore, the electrons are now towards downward by using Fleming's left hand rule. As a result, that is the flow of electrons, here is the flow of electrons which is opposite to that of direction of flow of current, and now due to that application of magnetic field, the direction of flow of that electron is downward, and electrons towards the downward. Now, electrons are accumulated in that lower region. Ultimately, holes are created on that of upper region. Therefore, a potential difference on that of two ends are developed. A potential difference at two ends now developed. That potential difference is nothing but Hall potential and is denoted by Vh, the potential difference. As Hall effect suggests, when a current carrying conductor or semiconductor is placed in a magnetic field which is mutually perpendicular to the direction of current, a current carrying conductor or semiconductor placed mutually perpendicular magnetic field, and what happened? A potential difference is developed at right angles to both the magnetic and electric field. So, a potential difference is developed on that of upper and lower ends. Now, that potential difference, developed potential difference at right angles to both electric field as well as magnetic field, that potential difference along y direction. Let me calculate mathematically what be that potential difference Vh, that is nothing but Hall potential difference. To calculating that, we know that when a charge carrier is moved on that of magnetic field, it experienced a force, and that force is nothing but magnetic Lorentz force. According to that magnetic Lorentz force, denoted by f of b, which is equal to charge, that is electron, its velocity, that is the drift velocity Vd, cross b, Vd b, sin angle between velocity and magnetic field, sin 90 degree. Vd is the drift velocity, that is F of B magnetic Lorentz force E Vd B sin 91. Vd is the drift velocity, Vd drift velocity of electron, drift velocity of electron. And the force experienced due to that of electric field, that is the Coulombic force. The Coulombic force denoted by Fe, that is charge E applied electric field E. Let we say that electric field is a Hall electric field E of S. E of S is the Hall electric field. Whereas E of S is equal to Hall electric field. Hall electric field. And is equation number 1. That one is, let equation number 2. At equilibrium, the magnetic Lorentz force F of B is equal to that Coulombic force F of E, or magnetic Lorentz force E Vd B is equal to Coulombic force E into EH. E cancel out, or Vd B is equal to EH, or V of D drift velocity is equal to EH divided by B. EH electric field due to that Hall effect, Hall electric field divided by magnetic field. At equation number 3. But we know the electric current in that of slab. Now the electric current in the slab I is equal to N E A V D, total number of charge carriers, electronic charge, area of that of slab, drift velocity, which implies I is equal to N E area as length into breadth, here length as W, thickness T, W into T Vd as area is equal to thickness into breadth. So area A is equal to thickness T into breadth W. Which implies drift velocity V of D is equal to I divided by N E W into T. That is equation number 4. From equation number 3 and equation number 4. From equation number 3 and equation number 4 we get ES by B is equal to I divided by NE WT. As we know, V of H is the Hall potential. V of H is the Hall potential. Potential as electric field into distance. So, electric field, Hall electric field EH into distance, the distance as W. Therefore, in place of EH we can substitute VH by W. In place of EH we substitute VH by W. W B as I divided by NE W into T. W cancelled out on that of both denominator sides. We obtain V of H is equal to one divided by NE I into B divided by W will cancel out T, or VH is equal to 1 by NE, that is RH Hall coefficient, into IB divided by T, whereas RH is equal to 1 by NE, that is the Hall coefficient. That will be the expression for Hall potential or Hall coefficient. RH is equal to VH into T divided by I into B. VH with the Hall potential, RH that is the Hall coefficient. Now we can calculate electrical conductivity. We know current density is equal to current per area. Current density J is equal to current I by area A, or J in terms of electric conductivity as sigma into electric field intensity due to Hall effect EH. So, I current divided by area as W into T. So, W into T. Therefore, electric conductivity sigma is equal to I divided by E H W into T. Whereas sigma electric conductivity. So, sigma is evaluated electric conductivity, here RH is the Hall effect. By using that Hall effect, we can easily say either that used semiconductor is a p type or n type. For that, we use that Hall coefficient. If R of H is positive, then it is p type semiconductor. If R of H is negative, then it is n type semiconductor. So, by using Hall effect, we can easily show what type of semiconductor is used. So, with the help of this video lecture, we understand the concept of Hall effect, what is Hall effect, and then calculating electric conductivity and Hall coefficient by the method of 4-probe method. We take a rectangular semiconductor slab having area A as its breadth W and thickness T. We apply electric field along x axis, magnetic field along z axis. Therefore, a potential difference is created along that of y axis, and that potential difference is known as Hall voltage. First, magnetic Lorentz force due to that of application of magnetic field, then Coulombic force due to that of electric field. At equilibrium condition, these two are same, and equating that, we have a Vd is equal to Es by V. But you know the total electric current in that of slab from that of definition, that is I is equal to NEA Vd, then the expression for Vd, and equating equation number 3 and equation number 4, and finally the expression for Hall voltage and Hall coefficient, then expression for electric conductivity. By using Hall coefficient, we can easily analyze what kind of semiconductors are used in particular situations. So, with this useful and informative notes, let me wind up this session. Thank you.